So, in order to start this conversation about figuring out how to find the area of stuff, we're going to be adding a lot of pieces. So, in math, sometimes we want to develop some new notation that helps us wrap our minds around adding a lot of pieces, right? So, that is where we introduce what we call sigma notation. This is the Greek letter sigma, a capital sigma, right? Um, and it is the Greek equivalent of s. And so because we're going to make a sum of terms, we are going to use this capital sigma, again, a capital S, in order to note the fact that I'm going to add a bunch of things. So the way this works is that um, the bottom part tells you where the index starts. The top part is going to say what number the index goes to, and then in front of the sigma, you're going to have the terms to add all together. So one example of this might be that I am letting this variable I start at 1 and go all the way to 3. But the terms that I want to add may look something like 2i. So what does this mean? Well, the first term where my index starts is I equals 1. So that term would be 2 to the first power. Well, then the next term is going to be, we're going to let that index increase by 1. So this is 2 squared, right? Now I is 2, so I plug 2 into this expression. So you have 2 squared. Now the index goes up 1 again to 3. So now you have 2 cubed, 2 to the third power, and that is where I stop because of the term on the top of my summation. So this sum is going to be 2 to the first plus 2 squared. Well, that's 4 plus 2 cubed. Well, hey, that's 8. So 2 plus 4 plus 8 is 6 plus 8 is 14. So it ends up being that the summation evaluates to 14. We don't really care about that as much as we just care about the ability to understand what this sum is trying to represent, what this sigma notation is trying to tell us. Now, similarly, I could have instead had my index start at 0 and then done 2 to the I and gone up to 3. Well, now my index starts at 0, so the first term is 2 to the 0th power, and then 2 to the first, 2 to the second, and 2 to the third. So again, just looking at that number up top doesn't immediately tell you how many terms there must be. Because if I start at 1 and I go to 3, well, yeah, there's 3 terms there. But if I start at 0 and go to 3, there's 4 terms, right? How many numbers if I start at 0 and end at 3? 0, 1, 2, 3. Um, yeah. So it is not that that is telling you that, right, the top number is not telling you how many terms do we have. This top number is telling us what number the index goes to, right? The last index number we plug into that index step right there. Okay, so this is sigma notation. And again, right now, this idea is just getting familiar with it. So what if now I wanted I starts at 2, I go all the way up to 5, and I am just going to add I. Well, I starts at 2, so first I have 2, and then we're going up 3, and then 4, and then 5, and I stop there because the top part, right, is 5. So this sum is how we would write 2 plus 3 plus 4 plus 5. Very good. Now, again, this is just a very soft introduction to sigma notation. Um, and we're going to kind of start off, right? This is a very gentle introduction, and now that we talk about the area problem, we're going to throw you very heavy into how we have to use and understand our sigma notation. So brace yourself, I guess is what I'm saying for the kind of stuff we're going to do with sigma notation. So this is 4.1, well, and we're starting to talk about something that we like to call the area problem. Well, what this is talking about is imagine the scenario where I have some graph of a function, right? Maybe it goes here like this, and I want to know the area of this shaded region here, the area between the function and the x-axis. Right, this can come from plenty of different ideas. Maybe you have some mechanical piece that has an odd shape, right? Um, and you need to know like the area of something that looks funny like this, right? Just weird shapes in general. Can I figure out the area for that? Well, there's no easy formula, right, to figure out the area of something that looks really, really weird, right? Apart from our basic geometric shapes, squares, rectangles, triangles, octagons. I'm drawing a pentagon, but whatever. Um, it's really hard to figure out the area of things. And even more so just the moment that our shapes get non-standard, right? So let's say instead of a regular pentagon, it has something weird like this, right? It has 5 sides, but the area of that thing is certainly a horribly weird question. Then finding the area for that is really, really difficult. So this is kind of the idea for here, for this section, is how can I find the area of really, really weird things? But in particular, we're going to look at this in the context of the graph of a function. How can I find the area of this shaded region? Well, the first thing that we're going to develop is this approach of looking at approximating the area using shapes that are really easy to figure out the area for, and that would be rectangles, right? So what is the easiest shape to find the area of? Well, maybe a square. Okay, well, filling this thing up with a square is pretty difficult, but maybe instead I use a rectangle. That way I can control the height of this thing. So let's say I wanted to break this up into 4 rectangles and approximate the area using these 4 rectangles. Well, what are the height of each of these rectangles, right? If this is h1, this is h2, h3, h4, right? Looking at the left side. Well, that is just going to be the function at each of these values right here, right? At each x value. If I'm looking at these left corners at the function, well, how do I figure out each corner? Well, how do I figure out the width of each rectangle? And that is the fact that I split this region into 4 separate pieces. So if this is A and this is B, my width here is going to be B minus A, right, the length of that interval, divided by 4. So that would give me the width of each rectangle, but then also tells me exactly how to move forward from each piece to the next. So the height of the first rectangle would be f of a. The height of the second rectangle would be f of a plus my width. And then the second would be moving forward by 2 widths. And then that fourth term would be what we get when we move forward by 3 widths. So these are the height of each one, but I want the area of the rectangle, so I multiply each height by the width. Well, then to get the total area, I would add each of these pieces together. Well, if I'm multiplying each of these by w, then I just as well may multiply w all the way on the outside here. So I get to write it like this. W times f of a plus f of a plus w plus f of a plus 2w plus f of a plus 3w, right on the inside of the function, and all of that gets multiplied by w, by the width of my function. So this would be this approximation for the area under the curve. But is that a good approximation? Well, maybe, but I think I could make it a little bit better, right? What if instead of using 4 rectangles, what if I split this up into even more of them, right? So for the same function, it looks like this, and I want the shaded region here. What if instead of breaking up into 4 rectangles, I broke it up into 8, right? Well, then these rectangles are much thinner, and I'm getting a lot closer to filling up the space with exactly as many, or exactly as much as I want, right? If we could see the area that we miss on each of these is what I'm filling in red, and then heck, I'll even fill in red here, the area that we overestimate. There's a lot less of that happening here, right? These tiny little pieces are really small. And so it turns out the more rectangles that I use to estimate, the closer I'm going to get to the actual area here. Well, this idea now is what happens if I let my rectangles, then, if I wanted to use an infinite number of rectangles, then my rectangles would have to be infinitely thin, but it would fill up that space perfectly. So I'm going to make an analogy here with talking about a jar and gumballs and marbles, right? So if I have a jar full of, right, these really big gumballs, and I'm trying to measure the size of the jar and right in terms of volume. Well, there's a lot of space between these marbles, or gumballs, I mean. There's a lot of space between these really large gumballs. So when I dump them all out and then figure out the volume by just counting how many gumballs I had, I'm going to be missing a whole lot of the space that is in here. So to that end, I think, okay, well, what if I find even smaller to fill the jar up? So let's use some like smaller pieces of marbles to fill the jar up, and I'll count those. Well, now once I do that, then my jar has less air in it than it did with those really big gumballs. So, because I'm using these smaller pieces, I'm going to get a more accurate idea of what the volume of this jar actually is. Well, what if I had some collection of tiny particles that were almost, as far as I can perceive it, infinitely small? Well, what would that look like? Well, hey, I kind of just described water, right? What if I took all of these marbles and made them so tiny that I can't even see how small these particles are, right? Something like sand or water, and then I fill the jar up, and if I know how much of this stuff that I have inside the jar, then I no longer am estimating the volume. I'm getting an exact perfect picture of the volume if I'm able to figure out the volume of whatever I fill it up with, right? So by using sand or water instead, I perfectly fill this up. How? My particles are, as far as I can tell, infinitely thin. So, by letting my rectangles become infinitely thin, and I fill this area up with those incredibly tiny rectangles, then instead of just trying to estimate the area, I should get what my area is exactly. The same idea of if I fill a jar up with water, a lot of particles that are infinitely small, not really, but right as far as we can perceive it, then this is exactly the volume of the jar is how much water it can hold. So that is our analogy here to what we're trying to build with our area, is I'm going to let this area be filled up with an infinite number of infinitely thin rectangles and see if I can calculate that, right? And again, this is calculus. We learned about limits at the beginning of the section, so maybe we can figure out what the limit as this goes to infinity actually truly turns out to be. Now, I actually did something very subtle, but I made a decision for us when we started looking at our rectangles in the shaded area. And that was how I placed my rectangles here. Not just the region, right, and how I divided the region, but specifically how I decided where my rectangles were going, right, what the height of my rectangles were. Because I looked at the left edge of the rectangle and went there, right? I made the left side of the rectangle match whatever the function is doing. But that may not be the case. Someone else may come along and say, well, I think it might work better if the right end of the rectangle is working. So what would that look like? Well, if we're marking along these same points and I go and make my right side match, then for this example, it would look like this. So maybe at first I'm underestimating, but then I start overestimating once my function is increasing. However, with the left rectangles, I start out overestimating and then I end up underestimating, right? So because of the fact that this function is kind of bending up and down, right, there's the weird concavity thing happening with this specific function. Um, this kind of changes whether my left or right rectangles, right sides, are going to over or underestimate. Now, what if you say, okay, I want to split the difference between the fact that my left rectangles are over and estimating some and my rectangles are over and underestimating in other places. Is there a way to balance this out? Well, hey, I have a left, I have a right, but just as, in traffic, it's not always a left or a right. Sometimes it's right down the middle, right? You don't always have to turn. You can go forward. I don't know why I'm making this analogy here. Um, we can choose to fit our height to be the middle of each rectangle instead. So in this case, if these are the widths of each rectangle, then I look at the middle and then make that my height. So now we can see almost in each of these rectangles I make, part of it is overestimating, part of it is underestimating, and that makes it so that each rectangle kind of balances itself out better. So again, this was left rectangles, these were my right rectangles, and these were my middle. Now, it turns out, again, the middle triangles is kind of the best method for approximating the area for these rectangles. Um, so if, we're doing this on our own, we would really want to use the middle rectangles if I really care about being really precise really quick. However, let's introduce some notation for the rectangles that we build. I'm going to write Ln, Rn, and Mn for the area found by using n rectangles to approximate, right? So when I write Ln, Rn, or Mn, then I'm going to use that method, left, right, or middle, with n rectangles to approximate the area. Well, can we come up with some formula for my left, right, and middle, right, respectively? Not one for all of them, of course, but one for each. Well, if I am looking at my left rectangle, right, and again, I'm going to call this A and this B, then one thing that is constant between all of these is going to be the width of each rectangle, right? All I'm changing in each of these scenarios are the height of the rectangle and how I figure that piece out. I am not, however, changing the actual width of these rectangles. Okay, so across all of those, we are going to end up with the same width. Well, again, if I start at A and I go to B, then the length of A to B, we're going to get B minus A, and then we're going to break that into n many rectangles, so we divide by n. Now we actually call this delta x. Why? Well, because that's the width of each of these rectangles. So how much do I move forward between each x value? Well, by the width of that rectangle. That is my change in x value across every rectangle. So we call that delta x because, again, in physics, we use delta to represent change. I'm not a physicist, not we. They use uh, delta to represent amount of change, right? So delta x also could be thought of as the width of our rectangles. Okay, well, for Ln, what is the height? Well, I'm going to start by looking at that leftmost value, right? So I'm going to start with f of a, but then I also want to move forward by one width and get, right, that next coordinate. Well, how much do I move forward if I go from A to the left part of the next rectangle? Well, A plus delta x. And then I move forward again, but by another delta x, so this one it's two delta x's, so on and so forth. So that's how I get the height for each of my left rectangles, but then I want to multiply all of that by the width. And again, using just this idea of the distributive property, I don't have to write that by, right, each and every one of my heights. I can just factor that out all the way out front. Well, hey, I'm adding a lot of pieces, so why don't I use my fancy new sigma notation to represent this? Well, I am going to add some number of delta x to each term, so I'm going to say delta xi, but for my first term, I'm not going to add any. So where do I start with? I has to be 0, but if I want n many rectangles, I just try to make that delta x look a little bit better. If I want n many rectangles and I start at 0, then how high do I go? To n minus 1, right? If I want 10, but I start at 0, that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That was 10 numbers, but I ended at 9. So because we start at 0 and we want n terms, we're going to end at n minus 1. So this, in sigma notation, is my formula for figuring out the left rectangle approximation. Well, now my right rectangle approximation is actually going to be really similar, right? I'm going to have the same width no matter what, and I want to plug something into the function. But for my right rectangles, I don't start at A, I already start having moved forward to this next edge. Well, then I move forward to the next edge, and the next edge, and the next edge, and the last edge, all the way through for all n rectangles. Which means the equation here would also be that I move forward by some number of delta x's. But where do I start at? Again, I start on the right side of that first triangle, or rectangle. I start at the right side of that first rectangle, which I get by moving forward by delta x from A. So the first term is going to have a delta x included, so the first term is going to start at I equals 1. Well, then if I want n many terms and I start at 1, then I'm going to go all the way to the nth term. So the only difference between my left and right rectangles is going to be whether I start at A and then go to n minus 1, or if I start at A plus delta x, and then I just go up to n, right? So these look a lot alike, except for the indexing. Well, then how can we represent the middle rectangle some way? Well, again, these are still going to have the same width of delta x, and I still want to plug something into the function. But for my middle rectangle, I'm going to start right here. Well, how do I get that? Well, I start at A, and then I go forward by half of my distance. Well, hey, that just means I start at A, and then go forward by half of delta x. That's the term that I start at, and then I'm going to go forward by delta x for each of these. So we're going to have delta x over 2, right? So far this just gives us a starting point, and then we're going to move forward by delta xi to get the other midpoints. But again, because I want to start here, I don't want to start having already added one of these. On this one, again, I is going to be 0, and if I want n of these pieces that start at 0, I need to go up to n minus 1. So these are three formulas for finding, right, or setting up uh, how I can figure out the area using each of these methods, right, and this is all written in sigma notation, right, for n rectangles. Well, again, the idea that I talked about before is what if I can let my rectangles become infinitely thin? Then does this even make sense to us? Well, yeah, actually it turns out I can just take the limit as n goes to infinity of one of my approaches, and hey, what does that say? Well, let's figure out where this value goes as n increases without bound, as if I had infinitely many, infinitely thin rectangles. This does make sense to us. Now, not a lot of sense to us maybe yet, but these are limits that we're earnestly able to find and take. Um, However, right away, our methods of doing this are kind of limited to really, really nice and clean examples. Um, well, one last concept before we actually start trying to do those limits at infinity. Um, well, in each of these three methods, which one of these is better if we're going to let our limit go to infinity, right? Which method do I need to use if I'm letting my rectangles become infinitely thin? Well, here's an idea. If I have a rectangle and I'm either considering the left, middle, or right, but my rectangle becomes infinitely thin, then how different is the left, middle, or right really going to be as my rectangle gets thinner and thinner and thinner? All of those are actually going to converge to being the same thing. So it turns out for the exact area, it doesn't matter which setup I end up using, right? It turns out the limit as n goes to infinity of my left method is going to be equal to that limit as n goes to infinity of the right method is going to be equal to the limit as n goes to infinity of the middle method. So that middle method is better when we're actually calculating something by hand. It is going to be more precise. But once I take this limit as n goes to infinity, they end up all balancing out because these are infinitely thin rectangles. So the left, the middle, and the right don't really have a significant difference, right? They're infinitely thin, so the left, middle, and right are infinitely close to each other. So a little bit of a weird conceptual argument to make, but just something to point out is this fact. I can use whichever setup I want to take the exact area, to find the exact area of this thing under the curve, the shaded region under the curve. Now, for these kinds of problems, we actually need some like pre-existing information. So, uh, someone really smart a while ago figured out this sum. If we take I terms, right, this sum, sorry, not I terms. If we take n terms where we're cubing I across the sum, then it turns out this actually can be found not just in terms of I, or as this sum that we just don't know how to figure out yet, but we can write this in terms of n. We can write this as something simple that we can, figure out and use. And so it turns out that the sum is equal to n squared plus or times n plus 1 squared all over 4. So we're going to use this tiny piece of information to find the limit as n goes to infinity of ln of the function x cubed on the interval from 0 to 1. So find the area under the curve of the function x cubed from 0 to 1, but using this definition with the area problem. Now, there is a little bit of a silly subtle idea here that we actually want to use. This says find the limit as n goes to infinity of our left rectangles. However, well, we have this fact. I don't really need to use my left rectangles. I can use any method of rectangles. So would it help me to use a different method of rectangles for this case? Well, our Ln rectangles, our index starts at 0 and goes to n minus 1, but my right rectangles, my index starts at 1 and goes up to n. Does that cooperate a little bit better with this piece of information that we have right here? Index starts at 1, goes up to n? Yeah, absolutely. So for that reason, we're going to use this fact that, hey, I don't actually need to be left rectangles. I could also just be right rectangles and go from there. So this is defined, right, from the concepts that we figured out a bit earlier, right? Limit as n goes to infinity of delta x, the sum of f of a plus delta xi. I starts at 1 and goes up to n. Well, this is the general form, right? But delta x is just b minus a over n, which means we know what delta x should evaluate to, right? Or we can simplify what this evaluates to, because 1 is b, 0 is a, so really this is 1 minus 0 over n. Well, hey, that's just 1 over n. Well, again, a is 0, so I can also replace a, which is 0. So this is really the limit as n goes to infinity of 1 over n times the sum. I starts at 1, goes up to n. F of a is 0, so I won't even write it. Just delta xi. Well, delta x is 1 over n. And since we're multiplying by I, I'm going to write that as I over n. Well, hey, we're plugging these values into our function. Well, that's just x cubed, right? F of I over n is something absolutely that we can figure out. So I can even rewrite that as I over n cubed. Perfect. Well, it turns out also, right, n is not something that is needed to stay inside of the sum. So what I mean by that is n is some already fixed number that we already know what it is, right? We're just going to be multiplying or dividing by n cubed in this sum, right? Because this cube goes to both parts. So I can pull this n cubed out of the summation and write it like this. So because I have an n in the denominator on the outside already, and then I move 3 more to the outside, I'm going to end up with 1 over, 1 over n to the fourth. And then on the sum, my index parts are always staying the same, and then I just have I cubed left on the inside. Well, hey, it told us this neat fact up here that we're going to use this, so let's just replace that sum with the formula that it gave us. So this is the limit of, as n goes to infinity, of 1 over n to the fourth times n squared times n plus 1 squared over 4. Well, hey, I can distribute this n squared to both pieces. Limit as n goes to infinity. And I can write this n over 4 under here. So this is 4 n times 4th. Now n squared times n is n cubed. Oh, sorry. I also want to square the n plus 1 first. So this is n squared times n squared plus 2n plus 1 is what you get when you square that. Now this, then we can distribute our n squared to everything. Limit as n goes to infinity, 4n squared on the bottom. And now n squared times n squared is n to the fourth. 2n times n squared is 2n cubed. And then 1 times n squared is n squared. So this is now something that I can distribute, or sorry, break this division up across all of those terms. So this is the limit as n goes to infinity of n to the fourth over 4 n to the fourth plus 2n cubed over 4 into the fourth plus n squared over 4 into the fourth. Well, hey, n to the fourth divided by n to the fourth cancels, so we're left with just 1/4 plus n cubed cancels with 3 of the n's in the bottom, and 2 and 4 simplifies to 1/2. So this is 1/2 with n in the denominator, plus 1 on top cancels with 2 of these n's, and now we have that. Well, now if n is becoming infinitely large, then 1/4 is unaffected. 1 over 2n goes to 0, and 1 over 4n squared also goes to 0. So it turns out this is 1/4. We just did an absolutely crazy thing. We found what you get when you break up the area under the curve, x cubed, right, from 0 to 1, 0 to 1, and x cubed looks like this, right? We found the exact area of this shaded region, that really weird curve. It's not a curve that we can fit on a circle. We couldn't find this area previously using any other method. We just used a totally new method of finding the exact area by breaking this interval into an infinite number of infinitely thin rectangles and adding all of those together. And it gave us 1/4, which I would say is very astounding, right? That we're able to do that. Um, this is a big idea, right? This if this is coming if this feels okay to you, then I'd say you're doing amazing. Um, I imagine this is something that people naturally do struggle with, right? Um, so again, think about these things for a while. And yeah, we did have to use this magical fact that the sum of cubes, of n many cubes, can be thought of or rewritten in this expression, right? This was paramount to being able to simplify this kind of thing. Without that, right now, we wouldn't have any of method that we could have gotten to solve this. But yeah, it's just equated to writing this piece using the sums that we're familiar with and then taking this infinite limit. So in theory, all we're doing is adding and taking limits. Hey, we can do that. We feel great about doing that, right? Um, yeah, I say that jokingly, right? There's more complexity and nuance to this than just saying you're adding things and taking a limit. So yeah, this is new. Stare at this until, it feels okay and reasonable and you understand what in the world just happened here. Um, okay, but yeah, that's very good. That is how we can take limits as n goes to infinity of the areas here, ln, rn, or even mn, right? Because they're all going to be equal once the triangles, or sorry, once the rectangles become infinitely thin. Very good. That is what we are able to do so far for the sake of the area question. Um, now again, but I didn't do an example of actually like doing L3 of something, right? But this is totally something that we can do. We just break the interval up into 3 pieces and go on the left to find what the function looks like there. Go on the left for that rectangle. Go on the left for this rectangle. Figure out what each of these widths are, right? Whatever the length of this interval is divided by 3. Find out what each of these heights are, and then plug those in, right? F of A plus f of A plus delta x plus f of A plus 2 delta x, all of these heights, these 3 heights, then multiplied by the width of the rectangles. And then this is just taking that to the infinite extreme. Okay, so very good, very good.